Assalamualaikum warahmatullahi wabarakatuh and very good day. So in this video, I'm going to cover the inequalities. So we have two types of inequalities that we are going to use after this. So the first one is Cauchy-Zero's inequality. So in this case, we have a vector. So basically we have x from the vectors which has n dimension. So x1, x2, xn, and also another vectors which is the same dimension y1, y2 up until yn. So basically we have Rn here. So the inequalities say that if you take the summation of k from 1 to the n to the dimension n, and as k multiplied by yk, then you take square, it is also equivalent to, or it is less than, when you take the summation of 1 by 1 here. So here should be the brackets in front here, and then here should be a bracket. So if you multiply this one and with this one, this number should be bigger than this part. So this is what Cauchy-Zero's inequality say. So now we are going to look at the proof for this inequality. Okay, first of all, I'm going to define my function like this. So my function here is depend on the lambda here. So how do I define? It's in this way, where I'm taking the summation from k to n, and then this is my constant xk, and this is my variable lambda plus yk squared. Okay, now I'm going to take the square of the expression inside here. So when I take the square, you can use the formula that you learned in high school. So it's going to be xk squared lambda squared plus 2xk yk lambda plus yk square. So open the brackets here, or open the summation here. So we can do this manipulation because we are considering the Rn here. So that's why we can open the bracket like this, and this one should be okay. Okay, so rearrange like this. So if you realize that actually we have a quadratic function now. So if you can see here, this is lambda square, this is lambda, and we don't have any variable here. So this should be our a, b. So a as or we have usually you know it, a lambda square, b lambda plus c, where we don't have any lambda here. So therefore I'm going to denote each of the coefficient here as a, b, and c like this. So if you realize that when we when we replace a, b, c inside this equation, we are going to get f lambda equal to a lambda square plus b lambda plus c. Okay, now we have I wrote here it is more than 0. Why this function is always positive? Okay, so you can pause the video for a while and think why I say that this function is always more than 0. Okay, so if you realize that the function here that we define is based on our summation here, and if we look here, each of the summation or each of the component here, we squared it. So means that we always adding some positive number. So when we add positive number to a positive number to a positive number finitely, so at the end it always become a positive number. So therefore here, that's why we can say that the function f here is always more than 0 for any lambda inside the real number. So therefore, for the case of quadratic function, it is always more than 0, means that the function could be either this way or this way. So you cannot have the function like this, right? So always you have a smile function in our case. So to get a smile function like this, you cannot have a solution, or the graph here cannot across the y-axis. Sorry, cannot across the x-axis. So let's say that if this across the x-axis, then there is some part is become negative here. For example, you have like that and go up like this. Some part here is going to be negative. That is not a possible case. So that's why we always we always conclude that our function must be something like this or like this only. Okay, and we understand that based on our previous lesson, we know that if the graph doesn't touch the x-axis, mean that there is no roots, or only the maximum roots is equal to 1. So therefore, the only possible case is when we have the determinant less than or equal to 0, right? So here we have b squared minus 4ac should be less than or equal to 0. So just recall again what happened to if we have determinant more than 0. So actually, if we have determinant more than 0, then we have a roots. So what do we mean by roots? Means that the function cross the x-axis. So in our case, we can only have the function cross the x-axis only once, where in the case determinant equal to 0, but that one should be okay because it still satisfy our condition more than or equal to 0. Okay, so now we are going to we know that this inequality is satisfying, right? So I'm going to replace everything. So b with this summation for a and c like this, and then I will get this inequality based on the determinant here. So therefore, rearrange everything. So I'm going to get this part, and then it is proven that my Cauchy's is called inequality like this. So it is proven in this way. So now we are going to use this inequality to prove Minkowski inequality. So to prove the Minkowski inequality, so let us see first what is the Minkowski inequality. So Minkowski inequality is that we have a summation here, x plus y square. We take the sum k from 1 up until n and take the square root. So this square root should be less than, we take square root each of the xk each of the xk and yk here. So this is the Minkowski inequality. So to prove the Minkowski inequality, what we are going to do is that we are going to take the xk plus yk square here. So we are going to forget for y the square root over here. So we just consider the square, and then like previously we open the square here to get this expression, and then because this is only the finite case, we can open the bracket like this. So we will have the summation for xk square, xyk and yk square. Okay, so now what we are going to do is we are going to apply the last inequality, Cauchy-Schwarz inequality to get or to estimate this expression. So what I'm going to do now, so I'm going to copy the first summation like this, second summation like this. So just copy and don't do anything. So what I'm going to do, I'm going to apply the last Cauchy-Ceres inequality from here to here. So how do I apply this one? So you see that here, this from xk yk, so become xk square yk square. So I have a square root here. If you realize that in the Cauchy-Ceres inequality, we don't have any square root, right? But we actually have square. But this is actually how to say valid, because I can take or I can manipulate this Cauchy-Ceres inequality by the following way. So I'm going to take the square root over here and then square root over here. So I will get what I'm looking here. So this part should be less than this part. Okay, so applying the Cauchy-Ceres inequality, I will have this estimation. So I know that this xk square yk square is always positive. So for me, I can do manipulation like this, which is I can take the square root each of the summation here. So I will take the square root for the first summation and the second summation. So this manipulation we can do if and only if we are sure the part here is always positive. I mean the summation part here and this part is always positive. For example, if we have like this 16 square root of 16, so we can change it into the square root of 4 multiplied by 4. So I'm sure that 4 is positive, this 4 is also positive, and I can have this is actually 4, right? 2 multiplied by 2 is wrong here. So get square root of 16 equal to 4. So the same thing like this. So I can do if I'm sure that the part inside here is positive. If it is not positive, then I cannot do like that, because for example here like that, I start with square root of 1 here, and then I rewrite 1 into -1 and -1. So if I apply this formula like this, so I will have square root of -1, square root of -1. So I will have I multiplied by I, which is I square. So this is the imaginary number. So you have to recall again the complex number. And then I square is equal to -1. So the final conclusion is that 1 is equal to -1, which is not true, right? So that's why you need to make sure when you want to do this kind of manipulation, the object here and this part is always positive, then you can do. So if you realize that this one is actually, we can write in terms of square like this. So therefore we can write this summation equal to this summation, hence we can take square root both sides, we get the final answer. Okay, so I actually prepare you one assignment 1. So it is related to this inequality. So I will post that assignment into your e-learning, so you can look the assignment and submit it. Okay, so thank you for watching.